6 months ago, I got myself this Arduino kit and went through all of its main tutorials and dug into the numerous questions that popped up along the way. And the first thing I did was to light up a LED. A simple exercise, but already exposes why a resistor is needed and why polarity is important for these diodes. Then moved on to an RGB LED, which packages a red, green and blue LED that can be controlled independently, allowing for a wide range of color representation made possible using 3 pulse width modulation outputs from the Arduino. And here, 8 individual LEDs are controlled. Now, since there is a limited amount of outputs from an Arduino, we can attach an IC to extend the number of possible outputs at the cost of some latency. And this IC is essentially a very limited piece of external memory. You write into its buffer the outputs that you want to have, and then use a latch to make them all available in one go, just like double buffering in a video. Now, if we grab the same circuit that we had before to light up a LED and place one or more condensers in parallel with the LED, once we power the circuit, the LED immediately lights up and the condensers charge in tandem. But once the main power source is removed, the condensers start to smoothly discharge into the LED, creating a smooth fade out of their intensity. This is because capacitors are essentially energy stores, this is batteries, with consistent charge and discharge times. So here, I'm going to remove both of the capacitors, so you can see how immediately the LED changes its intensity. But if I put one of these back, and by the way, I had 2 before in parallel because their capacitance was summed up and the effect was more apparent, but regardless, you can see that now it's smoother. Here we have a single unit segment display, and we can't control it at the segment level. So each of those small bars and also the decimal dot that we'll see after can be controlled independently. And in this example, we sequentially write a set of segments that we perceive to be as digits. We can also create any patterns in whichever sequence and timing that we desire. Here we have 3 examples of some custom patterns. This is a rotation pattern, a figure 8 pattern, which I also define using a custom sequence, and an alternating pattern, just to show you that you can literally do anything with these. And here I also activated the dot that you can see there in the bottom right, which typically is used for a decimal separation. But here it's just used for demonstration purposes. The kit also comes included with the 4-unit segment display module, and we can think of it as essentially being 4 of these previous units glued together. So if we write the same patterns from before on this 4-unit segment display, we see this replicated on all units. And what I'm doing here is pulling out the contacts that signal to the display if a unit should be used or not. And these will be the same contacts that will individually control each of the units in the next video. So, in order for each of the units to present their specific segment pattern, we need to write the pattern and then select which of the units should have this pattern written to. Wait for a short amount of time, and then move to the next unit, where we'll do the exact same thing. Only this time, selecting the unit or units that should have this pattern written to. And here, I'm doing exactly that, and made each of the units represent a digit from an ever-increasing counter. And here we have a LED matrix module, and its input can be thought of as an explicit bitmap, where each of the pixels is either enabled or disabled. And to achieve a scrolling effect, we set an offset based on the value received by this potentiometer that I'm manipulating. Right now, I'm fiddling with the potentiometer wires, where the VCC and ground wire are at the top and the signal wire at the bottom. And notice that when the signal wire is removed and manipulated with my fingers, the conductivity through my body can also influence the signal, although it's just noise. Now we transition into the LCD display module. The scrolling effect is achieved by leveraging a functionality from the liquid crystal library. Here we are using a string of normal characters, but custom characters can also be used. In this case, the potentiometer is used as a signal of how bright we want the LCD display characters to be. From the guide it says, we should be careful not to use the UNO R3 board analog write function to generate a pulse to the active buzzer, because the pulse output of analog write is fixed to 500 Hz. I've just happened to use analog write, and this is the result of varying the pitch of the buzzer. By adjusting the frequency in which the buzzer is discretely triggered, we can achieve a perceived effect similar to pulse width modulation that we used before for controlling the multicolored LED's intensity. Only this time, it alludes to a sound that I find quite similar to how older computer and console games would make car engines sound. This drowned out noise is me placing my finger on top of the buzzer, which makes it sound like it went underwater or something similar. Here we are using a sound sensor, and the red LED represents audio peaks and the yellow LED represents audio troughs. Testing, testing, testing. The tilt bolt switch component in the middle of the board consists of a very conductive sphere that is free to move inside the component's cylindrical shape. One face of the cylinder conducts electricity and the opposite does not. And here I'm just moving the board around so that the switch captures these two different states. When the yellow LED is on, it means that we have signal from the tilt bolt switch, and is off when the tilt bolt switch does not conduct electricity. This is an ultrasonic sensor that can be used to measure distances, and it's using a custom algorithm built from scratch because I wondered why an external module was required in the provided example code, since you just need to take into account the speed of sound and the time it takes for an emitted ultrasonic pulse to be received back by the sensor. I've validated the measurements using a real-life ruler, and they're actually accurate. No external code modules required. And here I'm testing how the implementation and module behave upon different configurations. including when the box is tilted sideways. Notice that when the box is tilted to the left, it measures 750 centimeters, since the pulses are deflected and to my left there's only wide open room, but to my right there is a wall, so it seemed to capture that shorter distance. Here, the yellow LED is enabled when motion is detected by the passive infrared sensor. Now, this is a really interesting module that bundles an accelerometer, gyro, and temperature sensor all in one place. And I've used the Arduino serial plotter tool to visualize the inputs along the different axes. And first we have the accelerometer, and now the gyroscope. While going through the datasheets of the module, I've noticed that it could be commanded to dispatch an interrupt signal whenever a certain threshold of movement was detected. This could be useful for low-power systems, for example, where the interrupt would flag that relevant movement data was starting and the main controller should transition from a standby state to a fully active and powered state. And here, the objective of this experiment was to make the blue LED blink whenever the gyro was disturbed. But this resulted in a mostly unpredictable output, as you can see from the random blinking. The LED doesn't quite blink at the same time when I disturb the module. Sometimes it does, sometimes it doesn't. And the root cause is likely because I was sending an incorrect combination of commands when setting up the module. So further exploration would be needed here. A photoresistor is a light-sensitive component whose resistance decreases when light hits upon its surface. If we place a wire connected from one of Arduino's analog inputs between the photoresistor and another fixed-value resistor, we are able to detect the resulting voltage drop caused by the component's variable resistance. And here, I'm using my phone's flashlight to demonstrate the effects of light on this component, which increases our light intensity reading shown in the LCD display. And now I'm blocking light from the photoresistor using my finger, which also affects its reading, as expected. With the exact same setup as the last video, save from the slight tweak on the script, by literally replacing the photoresistor with the thermosistor, which is yet another variable resistor but sensitive to temperature rather than light, we are able to measure ambient temperature which here I'm manipulating using my hand's warmth. So now the sensor is cooling off progressively after I stopped pressing it with my fingers. And I'm now attempting to cool it off further by blowing air into the thermistor until it reaches an equilibrium. While doing this experiment, there was some quite nervous plunging of the sensor into a tea mug filled with water, dangerously near to my computer. The more the water level sensor was submerged, the higher the value seen in the console there in the left. Now I'm removing the droplets of water from the sensor and showing the effect of pressing it with my fingers. I've yanked it out here by accident, but no problem at all. It can just be placed back in. The Arduino is designed to drive logical circuits with low output currents. So when we want to control a high-powered circuit, we want our Arduino microcontroller to control the valve, let's say, but not the pipes themselves. This is a perfect application for a transistor, or relays as we'll see afterwards, where the transistor offers a set of valve and pipes that either lets current flow through freely or blocks it completely. The kit comes included with two models of NPN bipolar junction transistors, the PN2222 and S8050. Both are often used interchangeably, as seen here in this video, but the PN2222 has a higher voltage rating to collector to emitter voltage, so 60 volts versus 25 volts, which in this case is not very relevant since we're not surpassing the 5-volt barrier. In these, the base is the valve, and the collector and emitter function as the pipes. Here we have the same setup as before, only this time we're driving a LED instead of a DC motor. And a potentiometer is used to regulate how open we want the valve to be. And again, same setup as before, but controlling a DC motor with the potentiometer. Notice that I was not using a flyback diode in the previous video to protect the circuit from back EMF voltage spikes, which happen when the DC motor is switched off. And it is not the wisest idea when performing multiple tests. I was not aware of that effect at the time, but fortunately no harm was done. And from this video onwards, this was fixed, and the proper protection was added. Here we are using the L293D, which is a neat IC that packs inside everything one needs to drive inductive loads, such as relays, solenoids, DC, and bipolar stepping motors, along with the bidirectional drive and overcurrent and kickback protection, so no flyback diode is actually needed on our circuit construction. Also notice that when attempting to drive the DC motor at low power, it struggles to start its rotation, but once power is increased or a slight nudge is given, it quickly starts to rotate freely. Relays are larger and have slower switching speeds when compared to transistors, but can handle higher current loads and higher voltages, while providing good electrical isolation. As a fun fact, in older cars, the tick-tock heard when activating the turn signal is actually the sound of the respective relay closing and opening the circuit to light up the blinker. Those relays are very similar to the one used here, and a similar noise can be heard in the video, as the relay closes and opens the circuit that powers the DC motor. When setting up a resistor and capacitor circuit, or RC circuit, we can take advantage of its predictable charging curve to delay the activation of a transistor, which in turn can activate another set of components. Depending if the transistor is a bipolar junction transistor, BJT, which is current controlled, or a MOSFET, which is voltage controlled, they would have different current or voltage thresholds at which they allow current to flow between the collector and emitter, in the case of a BJT, or drain and source for a MOSFET. In this case, a BJT has its base connected to the RC circuit, and upon its activation, a LED and DC motor are activated. Also notice that here I've learned my lesson, and here I'm using a flyback diode there on the left to protect the circuit against EMF voltage spikes. Notice that the DC motor either does not have enough power to start or barely has a delay once a smaller resistor is placed on the RC circuit, which I think to have been caused by having low capacitance capacitors and not having the ideal resistor being used on the RC circuit. But this would warrant further exploration and a deeper understanding of the problem. In this circuit, we have the same configuration as before, only this time there are two BJT transistors. One to drive the DC motor and another one to drive the LED. Servo motors are used in applications that require precise movements, where the motor's position, speed, and torque need to be accurately controlled. In this example, a button is used to switch between the state where the position of the servo motor is defined by the potentiometer and the state where the default servo motor position is set. Notice how the voltage noise resulting from the manipulation of the detached potentiometer wire affects the motor, and how the servo motor attempts to sync with these received values. The stepping motor is a clever piece of engineering that enables precision movement without the need of external feedback. In this setup, the motor is controlled fully by an automated script, and since the 9-volt battery was starting to die, it was powered through a power adapter. To the previous setup, we add a Rotary encoder to send precise commands of how much we want the stepper to move. This Rotary encoder is the same that you'll find in several appliances such as mouse wheels, car radio knobs, and washing machines. Notice that the movement is quite jerky, and no matter how much we move the Rotary encoder, only the most recent movements are actually accounted for. This is something that we'll fix on the next setup. To fix the previous behavior, this setup will use a script that takes into account all the movements from the Rotary encoder to establish a target rotation angle that every cycle the stepper motor will correct itself towards. But first, the Rotary encoder is not controlling any logic, and it's directly connected to these LEDs, just for demonstration purposes. Notice that the two LEDs are lighting up as the rotating encoder is manipulated, so that we can see which signals will be captured by our script. These signals consist of a predictable gray code sequence that lets us perceive with high accuracy whether it's rotating right or left. We'll now finish this demonstration and the LEDs are disconnected so that the main circuit is driven instead. Now we'll have the signals coming through our Arduino inputs, and we can interpret these signals leveraging upon the concepts that we've seen before. Plus, we also make sure to trigger the device interrupts not only for one of the inputs, as it was done on the previous script, but for both inputs, so that we can capture all movements correctly. As a result, the motor now precisely captures all the inputs we provide through the Rotary encoder. Here we are remotely controlling the stepper motor by using an IR sensor and its respective remote to produce the signals. Here I tried to punch in custom light pulses through a red LED emitter that could be interpreted as valid signals by the infrared receiver. But this would never work since this LED peaks at about 640 nanometers wavelength, which makes sense because it's meant to output visible light, whereas we would need a 900 to 1000 nanometer wavelength for an infrared receiver to pick up that signal. There are more details on the blog post about this. Now we'll use the RFID card reader to get the MIFARE contents from the two cards included with this kit. This setup is also able to read minimal information from other sources, like credit cards or electronic passports. Note that this module reference voltage works best when connected to the Arduino's VIN pin, instead of Arduino's 3.3 volt power output. This joystick module is essentially the same that is used in several game controllers, and its usage is fairly straightforward when using an Arduino. One of the peripherals you can provide as an input to the Arduino is a 16-button keypad that provides a useful human interface component for microcontroller projects. I've previously published a video that deep dives into how the keypad module works and how it can be controlled through a custom script without using any extra libraries. I've also went through the respective concepts and circuits, including how pull-up resistors really work. You can find the video link in the description below. A serial print not only sends structured information to the host through USB, but also through Arduino's TX output. The setup is very simple. It writes very long strings and individual bytes to the serial interface, using a very low baud rate, so that their individual bit signals can be roughly seen upon the right yellow LED that is attached to the TX output. The left green LED stays enabled before we start sending commands to the serial interface and is disabled once the writing phase is completed. Notice that even after all writes are committed, there are still bits flowing through the TX output. This goes on until Arduino's internal serial communication buffer is completely flushed. Building up on this, if we write individual bits by carefully timing a pin's output low and high to comply with the UART standard to form 8-bit packets, feed this through a wire to the Arduino's RX pin, read the resulting serial communication receive buffer, and then finally write these contents into the serial port, we are able to see this logged into the serial monitor. This was one of the most mind-blowing things while fiddling around with the Arduino. Using the serial monitor, we can easily send packets of information to the Arduino via serial communication. In this script, Arduino reads from the serial communication buffer and enables or disables the LED if the corresponding received information is a 0 or a 1. Building on this setup, we can use ATmega's integrated EEPROM to persist information. This means that even after a power outage, that information is still available, as seen here when I unplug the Arduino's USB power source. When plugged back in, it loads the previous state of the variable that drives the LED state, so we can see that the LED-enabled state was recovered upon boot. As seen before, we can attach an IC to extend the number of possible outputs by the Arduino. And here we extend the previous setup to support 7 different LEDs, although only 3 of them are shown in this video. And for this specific example, there's no real gain from using this IC other than demonstrating its usage, since we could have just drove these 3 LEDs directly from the Arduino's outputs. Here we send a command to the RTC module that forces it to output a 1 Hz square wave, meaning that the cycle of this wave repeats every second. Then, the signal is first connected to a LED, which leads it to blink every second, and then the output is directed towards Arduino's pin 8, thus showing this cycle's result on the serial output. We've now reached the final integration. This timer is the opus maximus of the provided tutorials provided by Elegoo. But there were components which were not working directly, namely the interrupt library. So I've adapted the provided example to use the built-in Arduino interrupt library and changed some of the connections, leading to a beautiful culmination of all the previous lessons, experiments, and explorations. This concludes our journey, but I'll leave you with the rest of this demonstration. Enjoy.